Greetings everyone. In this video we are going to do the actual coding. We are going to choose one of the pins of port B as output. We are going to configure it using the DDRB register, port B data direction register, and then we are going to write values to it using this port B register. Okay, now let's start drawing the circuit first before we write the code. I'll go to menu and I'm going to use this tool over here, simulIDE. This is something which you can use to simulate your microcontroller circuits. We'll see how to do that. So first let us pick the microcontroller from the components. We are using the AVR microcontroller, so click here, and the one we are using is 80Tiny45. so I'll just click and drag and this appears on the screen, right? You can zoom in by scrolling in and out. You can zoom in or zoom out. Okay, now we'll have to change some of the properties of this microcontroller. So to do that, click on it and choose properties over here. So by default the clock frequency will be chosen as 16 MHz for all the AVR microcontrollers. We are going to change that. We know that we are using the internal 8 MHz oscillator, which is then divided by 8 to yield a 1 MHz clock, which is supplied to the CPU. So the clock that we are going to use is 1 MHz. Change this to 1 and press enter. Okay, now let's go back to the components. We are going to connect an LED, so we can do that. We can connect the LED to any pin we want. Let's see, here you have B0, B1, B2, B3, B4, B5. B4 is close to the ground pin, so it will be very easy or convenient for me to connect an LED here. So I'm going to choose B4 as output, but you can choose whatever pin you want as output. There are no restrictions, right? Any pin from B0 to B5, any of those you can choose as output. I'm going to choose B4 as output. So now what I need is, I need a resistor. I'll tell you why I need a resistor. And then I need an LED, that's over here. Okay, I'll zoom out a little bit. I'll just move the components and I'll rotate this. That would look nice. I'll move it and keep it over here. Okay, the reason why we need a resistor is we should not directly drive the LED from the port pin of the microcontroller. That would usually damage the LED, because you are going to supply 5 volt VCC, so the port pins will swing between 0 and 5 volts. Applying 5 volts directly to an LED will surely damage it. So that's why you need a current limiting resistor. So if you put a resistor in series with the LED, there will be a finite voltage drop across the resistor, and the remaining voltage only will appear across the diode, the LED, light emitting diode I mean. Okay, usually you use 470 ohms, 330 ohms or 220 ohms for the current limiting resistor. I have a 330 ohm resistor with me, so that's what I'm going to use here. So I'll just change the properties, go to properties, and my resistance value is 330. Okay, and now we'll have to include the power and ground rails. I will do that. So I have ground over here. I'm going to click and drag. I'll place it over here, and then you have something called fixed voltage over here. I'm going to provide a fixed 5-volt supply to the microcontroller, so I will use this. I'll just right click on this, rotate. Now it looks nice. Okay, now let's start connecting everything. Ground and B4 I'm going to give to the 330 ohm resistor. This I'm going to connect to the anode of the LED, and the cathode of the LED I'm going to connect it to ground. So whenever B4 is driven high, there will be 5 volts between B4 and ground. Some of the voltage gets dropped across 330 ohm resistor, and the remaining voltage appears across the LED, and that will turn it on. Okay, now our circuit is complete. What I'll do is I'll just save it somewhere. I'll create a new folder called blink, and I'll save this over there. Okay, right. Now our circuit diagram is complete. So what we'll have to do is we'll have to start writing the code. For that, you need to have one more thing, that is this one. You remember in the first video when we installed everything, I also asked you to install AVR libc. What this is this is something like a standard library. It provides you a lot of header files and library functions, which makes it easier to program your AVR microcontroller. But this is not necessary, right? You can even program your AVR microcontroller without using libc, but usually that is not recommended, because that will be like you are reinventing the wheel. When you have library functions, standard library functions for doing something, the best thing would be to use them, because these library functions have been written and tested over many years by many people. So the chances of there being a bug or anything will be very less. In contrast, if you write your own library function, then most probably there will be bug in it, right? So it will be best to use this one. Okay, so this is the link for this AVR libc home page. I'll also be sharing the link in the description below the video. You can click on it and bookmark this thing, right? So we are interested in this one, the online users manual. You can also download it if you want by clicking on this PDF, right? I'm going to use the online users manual now. So if you click on it, it will take you to the AVR libc page, right? And it lists all the devices that are supported here. Our device is ATtiny45, right? So it's over here, see, ATtiny45. So our device is supported, and we can very well use AVR libc. And here you can click on this library reference. This will list all the header files that you are going to use. Okay, for example, if you want to use a delay, you will be using this header file. So you can click on it and have a look at what are the macros and functions defined within the header file. Okay, let's go back. And for GPIO we will be using this one as well, avr/io.h. It contains AVR device specific definitions. Okay, so for example, if you want to program the data direction register of port B, you need to write to this register DDRB, right, which is at this address 0x17. The macro definitions of DDRB and the individual bits DDB5, DDB4 and so on, all this will be defined within the avr/io.h header. Okay, so whenever we are programming GPIO, we will always be including this. Okay, avr/io.h. And then if you want to use a delay, you will be using this header util/delay.h. Okay, so for the code that we are going to do, we will be using these two headers. Okay, enough talking, we'll get started. So you create a project somewhere. Okay, I have created a folder called YouTube, and within that folder I am going to create a folder called blink. Okay, this is where I am going to store all my project files. I have already stored that circuit which we have drawn over here, right? I have already stored that over here. Now what I want to do is I want to create a new file. Okay, I will right click, create document, empty file, and I will call it blink.c. Okay, I'm going to open the file. So when you're programming, you always have this AVR libc by the side. You can use it as a reference. Okay, I'm going to start with a comment. It's always recommended to do it this way. So whenever you start programming, you include a comment which contains some information like who is the author and description of what this file is about. Okay, so author, okay, that's my name, and then description. So description is I have connected an LED to PB4, so I want to turn on and turn off this LED. Okay, so turn on and turn off an LED connected to PB4, and I want it to go on and off every other second. So the frequency is once per second, right? So I'll write with the frequency of 1 Hertz. Okay, so one time every second it will be on. Okay, now in order to write to a particular port, we need to configure some registers, right? So this is PB4. I need to configure DDR4, this one over here, DDR4, and then port B4, right? So I need macros for these things, for the data direction register as well as the port B register. So for that I need to use the avr/io.h header file. So I'm going to include it, hash include avr/io.h. okay, now I'm going to write my main function, void main, open and close brackets, okay. So first thing what I want to do is I want to configure PB4 as output, and then what I want to do is I want to write logic 1 to PB4. Then I want a delay of 1 second. Then I want to write logic 0 to PB4. This will turn off the LED. Then again I want to delay by 1 second. Okay, this configuration step, it occurs only once. So once you configure PB4 as output, it's going to remain that way. But these things, these steps, writing 1, delaying 1 second, writing 0, delaying 1 second, these things should occur repeatedly as long as the circuit is on, right? As long as the microcontroller is on. So what I want to do is I want to put all of these into an indefinite loop while 1. So now what will happen is these things are going to occur repeatedly, right? Indefinitely till you turn off the microcontroller, right? Okay, now let's get started. So in order to configure PB4 as output, I need to write a value into the DDRB register. I need to write into which position, this one, DDB4, because I am using pin 4. While doing that, I should not disturb any of these other values. Okay, so we'll see how to do that. So I'm going to write a value into DDRB. Okay, so what I want is, I'll just put a comment over here. If you look at this DDRB register, these first 2 bit positions are unused because you have only 6 pins available for GPIO in the 8045 microcontroller. So these 2 values in positions bit 7 and 6, they are undefined. I'll take them as don't care, X. Okay, and then DDB5, it can contain any value, it can contain 0 or 1. Okay, but I don't want to disturb that value. Okay, I'll write a 0 over here. ddb4, this is where I want to write a 1. Okay, 1. Then you have what? ddb3, 2, 1 and 0. I'm going to make all of them zeros. 3, 2, 1 and 0. Okay, so I'll make this 0 as well. Okay, so what I want to do is I want to write only to ddb4 without disturbing any of the other values. So how can we do that? Because these pins, for example ddb1 may be configured as input, right? That means it should be held at 0. You should not disturb it by writing some value to it, right? So what we can do is we can use a bitwise OR operation. Okay, so what I will do is, let's say that ddrb has some value previously, for example xx followed by 1 0 1 1 0 0 1 1. Let's see how much values I have. 1 2 3 4 5 6 7 8. Okay, I'll make these 2 x's. Okay, let's say this is the contents of ddrb register, right? Now what I want to do is I want to change only bit position for ddb4. Okay, so this is 0 1 2 3 4. Okay, there's a 1 here. Let me write a 0 over there. Okay, I want to change only the value of this thing. I don't want to disturb any of the other things, any of the other bits. Okay, so try doing a bitwise OR operation. See what happens. Forget about the don't care bits. Okay, first 2 bits. Look at the third from the MSB. First 2 most significant bit positions, forget about them. Look at the third most significant bit position. It has 1, right? Here what do you have? Here you have 0. So 1, when you OR with 0, it gives you 1. So this bit is not going to get disturbed, right? Look at the next bit. What you have? You have a 0 here. So 0 is going to be ORed with a 0, right? So it's not going to disturb it. 0 OR with 0 is going to be 0. And then here you see you have a 0 here, and here you have a 1. So 1 ORed with anything, be it 0 or 1, it is going to turn it into a 1, right? And all these other things, for example look at the least significant bit. Here it is 0, here it is 1. 1 ORed with 0, it is going to be 1 only. It is not going to disturb those bits, right? So if you use bitwise OR operation, so only the bit that you want to change, that alone will get changed. All the other bits will remain unchanged. Okay, so that's what I'm going to do now. In ddrb, I'm going to do a bitwise operation of the ddrb register with a value. What value? With 1, just been shifted to ddb4. Okay, if you are wondering what is ddb4, look at the data sheet. This is ddb4. The bit at the 4th position in the ddrb register. Okay, so this ddb4, this is a macro which is defined in this thing avr/io.h. So if you want to use these macros ddrb and ddb4, if you want to use these symbols and all, you need to include this header file. Okay, right? So now I have written a 1 into the fourth bit position of the DDRB register. That means PB4 has been configured as a output. If you write 1, it will be configured as output. If you write 0, it will be configured as input. Okay, so when the microprocessor is reset, all these DDRB values will be 0. That is, all pins will be acting like input, right? So if you want to configure any pin as output, you need to deliberately write a value of 1 to that particular bit position. Okay, right. Now let's come into this while loop. So what I'm going to do first, I'm going to write logic 1 to PB4, fourth pin of port B, right? So look at the data sheet. You have a port B register, and the fourth bit is port B4, right? So I'm going to shift a 1 into this particular position, right? So I'm going to write port B R equals 1 shifted into port B4. Okay, same logic only. You are going to shift a 1 into this particular bit position without disturbing any of the other bits. Okay, let's skip the delay for now. I'll tell you how to write delay in a short while. Now we are going to write 0 to port B4. Okay, so this also what you need to do, you need to write a 0 without disturbing any of the other bits, right? So for writing 1 into a particular bit position, you are using the OR operation. For writing 0, can you guess what operation you are going to use? I will give you the answer, but you try to figure it out yourself, right? If you have any questions, you can get back to me in the comments and I will answer it. But it's very simple, very easy logic only, right? So what I'm going to do is, port B, instead of OR, I'm going to use AND. I'm going to AND the contents of port B register with the complement of this thing, the complement of this one. Okay, now to understand why I did that, you need to look at the truth table of the bitwise AND operator. So if you do bitwise AND of any value with 0, the result will be 0, and if you do a bitwise AND of any value with 1, the value will be preserved. Okay, that's the reason behind it. Try to figure it out. Okay, now we'll come to the delay part. So I want a delay of 1 second, and for that also you have header files and library functions, right? So go to this util/delay.h. it's taking some time to load. Okay, so this page has loaded. Okay, util/delay.h. So here you have two functions, delay ms and delay us. This is for millisecond delay and this is for microsecond delay, right? I want a delay of 1 second, right? Delay of 1 second. So 1 second would be 1000 milliseconds. So I'm going to use this function. So if I want to use this, I need to include this macro f_cpu, This f underscore CPU is the CPU clock frequency. So we know that we are using the internal 8 megahertz clock, which is divided by 8 and then supplied to the AVR CPU core. So 8 megahertz divided by 8 will give you 1 megahertz. So we are going to include that over here. So hash define f underscore CPU 1 followed by 6 zeros, 1 2 3 4 5 6, and it's an unsigned long, so I'm putting UL over there. Okay, now you can come down here and use the delay ms function. So underscore delay underscore ms 1000. So this will give you a 1 second delay. So after I write 1 into PB4, I am waiting for 1 second. Then I write 0 to PB4 and again wait for 1 second. So underscore delay underscore ms 1000. Okay, so whatever is inside this while loop, it should repeat again and again, right? That's why it's an indefinite loop. As long as the microcontroller is powered on, this will keep happening. 1 will get returned to PB4 and the value at PB4 will stay 1 for 1 second, and then 0 will get returned to PB4 and the value will stay at 0 for 1 second, and the whole thing will repeat again and again. Okay, so now we are done coding. Okay, what we have to do now is compile. So I'm going to go to the folder where I created this file, right click, open in terminal. Right, so now watch carefully and note down the command that I am typing. I'm going to invoke the AVR GCC compiler and specify the clock frequency and the output file and the input file, and this should be followed by the microcontroller that you are using. That is very important, right? So follow along and note down what I'm going to do, right? So the compiler is AVR -GCC, and then I'm going to optimize it for size. Okay, so -OS. Then I need to specify the CPU frequency. So for that I'm going to put -F CPU, that is equal to 1 megahertz, 1 followed by 6 zeros, 1 2 3 4 5 6. It's an unsigned long value, right? The output executable file that I want is specified by -O, and I want to call the file as blink. The input file is blink.c, and the microcontroller that I am using, we need to specify using -MCU. This is the microcontroller we are using, that is AT-Tiny45. Okay, so again I will tell you what all this thing is. This is the compiler that we are going to use now to compile our code for the AVR microcontroller, and I am optimizing for size, so -OS, and then I need to specify the CPU frequency, which is 1 megahertz, and then I need to generate an output executable file from the input file. Input file is blink.c, output executable file I'm specifying by -O, and I'm calling it blink. The MCU for which I am compiling this code is AT-Tiny45. Okay, now hit enter. Let's see what happens. There seems to be a problem here. undefined reference to delay ms. I think I didn't include the util slash delay header. Let's check. Yes, I didn't include it. Yeah, this is what I have done. So if you want to use these macros fcpu delay ms and all, you need to include this header file. I forgot to do that. So hash include util slash delay.h. okay, I will save it, and then now I will compile again. There seems to be a problem with the fcpu. Another warning, fcpu is not defined. Okay, let's check the code again. Looks like I have defined it. Let's see. Hash define f underscore cpu. Oh, I need to define it before this include file. Okay, just a small mistake. Cut it and put it over here. I think I have saved it. Yeah, I have saved it. Okay, I'll compile it again. Yeah, now no problem, right? So the first thing that I forgot to do was I used this library function without including the header in which it is defined. So good that I got these errors, right? So that you will also know what the importance of using header files, right? The second thing that I did was I had to define f underscore cpu before this header file. That I did not do, right? Okay, now everything is compiled. Let's see what files we have. I'll do an ls. You can see something green over here, right? This is the executable. This is my input file blink.c, and this is the executable that I generated from this C file. And let's see what type of file it is. We'll use the file command, file blink. See, this is an ELF 32-bit executable file, atmel avr 8-bit version. Okay, but the thing is, the programmer that you are going to use, the software that you are going to use to program is avr dude, and that software will accept only hex files, intel hex files, not elf file. So we need to do one more thing. We need to convert this elf file into a hex file, intel hex file. So make a note of the command that I am going to use now. It is very important. You will be using this for all the exercises that you are going to be doing, right? So the command is avr -obj copy, and we are going to remove a section from this elf file. So we are going to write uppercase r dot EEPROM. We are going to remove this section, and the output file that we want is intel hex file, so I hex, and the input file is what, blink, and the name of the output file, I'll keep it the same, blink.hex. okay, so are you able to understand this command? So we need to invoke this command avr -obj copy, and we are going to remove the .EEPROM section from the ELF file. So I am using -r .EEPROM, and the output file that I need to generate is going to be intel hex file. So it is IHEX -o IHEX, and the input file is this thing, blink, this green color blink executable file, and the output file name that I want is blink.hex. Now I'll hit on enter. Okay, now we'll do an ls. See, you have an executable file, blink.hex. We'll check what type of file it is. File blink.hex, right? So it's a ASCII text. This is what we need. Okay, so now we are done. So we have written a C program for blinking an LED connected to PB4, and then we have compiled it. The compiler gave us an ELF file. We wanted a hex file, so we converted the ELF file to a hex file. Okay, and now let's see if everything works, right? So before we actually program it, we will be doing that in the next video. In this video we are just going to check if everything is fine. Okay, so for that we are going to include a firmware for this 80Tiny45 microcontroller in this simulIDE, right? So let's check the property, see if it is 1 megahertz. Yes, it is 1 megahertz. Okay, so now what I'm going to do is I'm going to right click on this microcontroller, and then here I have an option called load firmware. This firmware is nothing but the hex file that we generated just now. Okay, I'm going to load it into this microcontroller and click on this, go to AVR project. This is the folder that I created now, and here you have the hex file. Double click on it. Okay, the firmware is loaded. Now I need to power on this microcontroller, and I'll run it. Let's see what happens. See, you can see the LED is blinking every second. Are you able to see it? See, our code works. And you can do one more thing. You can also monitor the special function registers. What are the special function registers that we are using for this program? We are using just two, DDRB and port B. So I can click on RAM table and type the register name DDRB and click enter. See, this is the value written into DDRB. This is bit position 0, 1, 2, 3, 4. Okay, this is the MSB and this is the LSB. It's showing in the reverse order. Okay, so it is following the big Indian notation, not the little Indian notation. So I shall count from this thing. This is 0, 1, 2, 3. Oh, sorry, I made a mistake here. No, it's little Indian notation only. So this is bit 0, this is bit 1, bit 2, bit 3 and bit 4. So that's what we are using, PB4. Sorry for the confusion. So 1 is written into PB4, right? So that means what? If you write a value of 1 into the DDRB register, that particular pin will be configured as output. So PB4 is output. Now let's monitor port B. So I'll click here and write port B. See what happens. Every second that one bit, just that one bit or not any other bit, that one particular bit which we have configured as output, it becomes 1 and then becomes 0. It keeps doing this forever because we have included this particular code inside a indefinite loop, while one loop. Okay, so whenever it becomes 1, the LED turns on, and whenever it becomes 0, the LED turns off. Okay, great. Our code is working as expected. In the next video we will see how to use the AVR Dude software to flash the microcontroller and then test if it works in the real world. Okay, right. And before ending, I'll just save this. Okay, saved it, and I'll stop the simulation. Okay, thanks for watching. I'll see you in the next video.